Hello, this is T. Anil Raju, Signal Processing YouTube channel. In this class, I want to explain about digital signal processing topics. So, consider this one as a course, and I am discussing about discrete for how to compute 4-point DFT of a sequence x of n. The given sequence is 1, 2, 3, 4. Here number of samples are 4 and small n varies from 0 to 3. So, we consider in the sequence notation 0 is the first sample, and like that we will continue, and the last sample here is in the index 3, the value is 4. How to compute this one? So, computation will be having this x of k. First we will write the formula, and before that we give the information how many number of samples are there, what is the capital N value. Here we have 4 samples, that is why capital N value is equal to 4. X of k, the formula is 0 to 3. Why? Because here capital N is 4, 4 minus 1 is 3. X of n, W n k of 4. And we have some steps here. We have to follow that steps. First, we have to expand the summation by substituting the n value. We get the this equation. Once if you substitute the n value, then we simplify that one. Then we get a simplified version in terms of k. Now, x of k is this sequence. This will be the standardized one. For k different values, we will get the x of k. So, I am just explaining for different values of k, just simply substituting k value 0 in the earlier equation, we get this 1 plus e power omega 0 of 4 plus 3 capital W of O 4 plus, like this. When you substitute W O of 4, the value is 1, and by simplifying that we are going to get 1 plus 2 plus 3 plus 4 is equal to 10. Similar way, we have to calculate for other values of k. K is equal to 1, what will be the solution? Here the difficult thing is how to expand this W and getting the value. So, W, capital W is given with e power minus j 2 pi by capital N. So, based upon that we have to calculate the value, and for k is equal to 1, we got a value of minus 2 plus 2j. For k is equal to 2, we get minus 2. For k is equal to 3, we get a value of minus 2 minus 2j. We can see here the output is a complex number. That is what we can have in a statement, that when we find the DFT of x of n, the frequency coefficients are complex. So, we get in a complex values, and we can identify that how many number of samples in time domain, the same number of samples in frequency domain also we will get. But to evaluate this one, it is very difficult to represent the complex numbers. So, that is why we find the magnitude response and phase response. In the next slide, we will see about magnitude response and phase response. Magnitude response is nothing but taking the mod of the x of values, x of k values. So, here we have in the solution 2 real numbers and another 2 are complex numbers. So, the magnitude of the real number will be the same, but when we come to complex number, we use a formula that real term square plus imaginary term square. By using this formula, we will simplify that complex number, and we will get in a magnitude of that one. So, finally, we got the magnitude response of the frequency x of frequency coefficient x of k, we can call that our magnitude response, or we can call the magnitude spectrum. The final solution for the signal x of n of samples 1 comma 2 comma 3 comma 4 is equal to 10 comma 2 root 2 comma 2 2 root 2. So, these are the 4 samples. So, coming to the phase spectrum or phase response, so we find the angle or phase. For that we have in a formula tan inverse of imaginary term by real term. So, by using that formula we will calculate the phase response also. So, in conclusion, what we can tell is a DFT computation will require some steps. First, we have to write the formula, then we have to see what the samples given, how many number of samples are given, then substituting those values and expanding the summation is the first step. After getting the summation equation in terms of k value, then we will try to compute the x of k by substituting k value, different k values. So, finally, we will get a complex number, but that complex number will be not represented directly. So, we will take the magnitude response and phase response. Coming to the another problem. So, this problem is inverse discrete Fourier transform. What exactly we do in the Fourier transform, discrete Fourier transform, the same steps we also do here, but the formula will be different. As I told earlier that the difference between DFT and IDFT are they are conjugate to each other, and the given signal here is x of k. So, here we have to convert the frequency domain coefficients to discrete domain coefficients. The formula is first written. We will write the first formula, and we will take the data, how many sample frequency coefficients are there. Those frequency coefficients samples will be calculated as capital N, and we will substitute the formula. So, in the left hand side we will take x of n, the time domain sequence, and 1 by n. So, this 1 by n is in a normalization factor. So, when we are finding this inverse DFT, after getting the values, we are going to normalize that values with a capital N number of samples. So, that is why this 1 by n parameter is known as normalization parameter. And here also, first we expand the summation by substituting different values of k, then we will get one standard equation in terms of n. Earlier we get the same in terms of k, but here as we are taking the summation in terms of n value, k value, we are substituting those, and we will get the standard equation as n. Then we will find for every value of n by substituting 0, 1, comma 2, comma 3, and here if you see for n value 0, if you substitute we get a value of 1. That means nth sample, if you take n is equal to 0th sample, the x of 0 is 1. Similarly, x of 1 we will get 2, and for x of n is equal to 2 we will get 3, and x of n is equal to 3 we will get 4. So, finally, the inverse DFT of capital X of k equal to x of n equal to 1 comma 2 comma 3 comma 4. If you observe this, this is wantedly taken an example. I have taken example 1 with the time sequence of x of n 1 comma 2 comma 3 comma 4. I got a frequency coefficients 10 comma minus 2 plus 2j minus 2 minus 2 minus 2j. So, what in the second example we observe is the same frequency domain samples is given to the to compute IDFT. The answer we got is x of n is equal to 1 comma 2 comma 3. That means, if you give a time signal, if you convert the Fourier coefficients and finding the Fourier coefficient for that one, we will get the same time domain signal. So, this is what about DFT and IDFT. Coming to the revision, what I discussed in this class is, first I started with defining the discrete Fourier transform, then how to compute DFT, definition and formula part I discussed. Later I discussed about inverse discrete Fourier transform and relation between discrete Fourier transform and discrete time Fourier transform, DTFT and DFT. Later, I have considered two examples. For one, how to compute DFT, and another one is how to compute IDFT. And we observe that if you give a time domain signal and compute DFT, we get frequency coefficients which is complex. If you give that complex coefficients again to IDFT, we get the frequency, we get the time domain sequence. So, they are conjugate. Why we are getting this means because the basis function what we used in discrete Fourier transform and inverse discrete Fourier transform are conjugate to each other. And with this I am concluding this class. Thank you.